Alright, in this video, as you can see on the board, I'm going to be taking you through the comparative chemistry of the aliphatic hydrocarbons. Comparative chemistry of the aliphatic hydrocarbons. Yes, what are the aliphatic hydrocarbons? If you can recall, we have treating organic chemistry. And when we say organic chemistry is the chemistry of some group of compounds known as organic compounds. And these compounds are made up of solely carbon. Carbon bonding with itself, catenation. Carbon bonding with hydrogen, called hydrocarbons. And carbon bonding with other elements, called non-hydrocarbons. But in this video, I'm going to be treating the hydrocarbons. And the hydrocarbons is divided into two, the aliphatic and the aromatic. The aromatic are known to be cyclic and has a closed end, while the aliphatic are known to either be cyclic, branch, or unbranch. They can be straight, they can be branch, unbranch, and they can be cyclic. But aromatic compounds are strictly cyclic, and they are all example of hydrocarbons. But in this tutorial, I'm going to be just focusing, streamlining our attention only on the aliphatic hydrocarbons. And when we say aliphatic hydrocarbons, we are simply talking about our alkanes, alkenes, and alkynes today. So when we say comparative chemistry, it's a chemistry that compare two or more things. So as a chemistry student, it is important that you know how to strategically compare the three aliphatic hydrocarbons. To continue in this video, I'm going to be proceeding to compare the three aliphatic hydrocarbons, alkane, alkenes, and alkynes. So, owing to the general formula, as you can see on the board, I have CnH2n plus 2 for alkane, CnH2n for alkane, CnH2n minus 2 for alkynes. What many students did not know about this general formula is that they are actually derived from one another. So, alkane is the first known organic compounds, being the first in the aliphatic hydrocarbon division. And the second known organic compound, group of organic compound, is the alkenes, the ENE guys. Alkane, ANE, ENE, and alkyne, YNE. So alkane is the mother of all organic compounds, having the molecular formula of CnH2n plus 2. While alkene, on the other hand, is the next after alkanes, and it was derived from alkanes by subtracting 2 hydrogen. So if you look at this formula, CnH2n minus 2. So when we subtract 2 from the CnH2n plus 2 cancel minus 2. That is what leaves us with CnH2n. So when you delete this last plus 2 from alkanes, then you are getting alkenes. And in the last guy, the alkynes, which is the last of the aliphatic hydrocarbons, you continue to subtract another minus 2 from the formula of the previous. So alkyne is derived from alkenes, while alkene is derived from alkanes. So when we have the alkene, this is the formula for alkene, ENE. When you minus 2 further from the CnH2n that you're having here, then you have your alkynes. So that is the formula. The formula goes thus: CnH2n plus 2. You will when you remove these 2, then you have alkene, CnH2n ordinarily. Why when you want to have alkynes, the formula for alkene, CnH2n, then you subtract minus 2. But if you want to get alkynes directly from alkanes, if you want to get alkynes directly from alkanes, so instead of waiting for the formula of alkane to minus 2 from it, then minus 4 directly. If you minus 4 directly from here, you are going to be having plus 2 minus 4 is what? Minus 2. Then you end up having CnH2n minus 2. Just know that in hierarchy, alkane has more hydrogen than alkenes. Then alkenes has more hydrogen than alkynes. All right? As they begin to increase, then as they begin to discover more organic compounds, then the number of hydrogen begin to decrease. So this is a representative member. This is the formula for ethane. This is formula for ethane, and the formula is C2H6. Why? There's a Greek numbering. There's a Greek alphabet. Et in Greek means 2, and that means this Greek naming suggests to you the number of carbon. So if you hear et, it means 2 carbon. So that's how I know that ethane will be C2. Now, how do you get the number of hydrogen? According to the formula, the number of hydrogen is twice the number of carbon, which is 2n plus 2. So if you twice 2, you get 4. 2 times 2, 4. Then you have to add 2 if it is alkane you are trying to create. That will now be 4 plus 2, 6. So to get the number of the hydrogen, you have to first get the number of the carbon as suggested from the name of the compound you are trying to create. Then you must add 2 extra after you have doubled it. So 2 times 2, 4 plus 2, that's 6. But for you to get the alkene equivalent of that ethane, which is 18, for us to get 18 now, we are just going to focus on the number of hydrogen. So we are going to reduce this by 2. That is the alkene equivalent. So that means for alkene, it's having lesser number of hydrogen compared to alkane. So ethane is having more hydrogen compared to alkene. It means ethane is 2 hydrogen lesser than ethane. And then for the last guy, which is the alkene equivalent, the alkene equivalent will now be what? And the alkyne equivalent, sorry, the alkyne equivalent will now be ethyne. And it's going to be 4 hydrogen less than alkanes because it's too far from it. And then it's going to be 2 hydrogen less than alkene. That's how you create. For me, if you may ask me, the best way for you can learn this thing is that you first just understand how to get the number of alkanes. So to get the alkene and alkyne equivalent is very, very easy. To get the alkene equivalent, just minus 2 from the number of hydrogen. The number of carbon will remain the same for every one of them. Then minus 4 if you want to get alkyne directly from alkanes. Then minus 2 if you want to get alkynes from alkene. So ethane is C2H6, ethene is C2H4, while ethyne is C2H2. Now, this formula that you see me draw on the board is just what we call molecular formula. Molecular formula will just shows us the number of elements that are involved. So this molecular formula is telling us that in this compound ethane, there are only 2 carbon altogether, and there are 6 hydrogen altogether. But there's another type of formula that we call, this one is MF, molecular formula. There's another type of formula we call structural formula, SF, structural formula, and it can be in different form. It can be dash line formula, it can be structural formula that use dots. We used to call this one Lewis structure, and then it can be condensed formula. You can condense it and you can expand it. They are all structural formula. And the kind of bond that are involved in hydrocarbons, since hydrocarbons solely involve carbon and hydrogen, it means the fight, the argument is just between carbon and hydrogen. And if you check the periodic table, carbon is in group 4, while hydrogen is in group 1. This group 1 and group 4, they are group that does not have lone pair. And when it comes to chemistry, what gives you extra advantage is you having lone pair. And lone pair started from group 5, 6, 7, and 8. From group 1 to 4, there's no lone pair. That means in terms of hierarchy, carbon and hydrogen are somehow close. In fact, if you check their electronegative value, go online and search for it. The electronegative value of carbon and hydrogen are somehow close. Therefore, they are the bond that we exist between them is called non-polar bond. And in a non-polar bond, please write it down if you can pause the video. In a non-polar bond, electron or atom are shared equally. So if you want to share this 6 hydrogen with these 2 carbon, you are going to share it equally. For you to write the structural formula in a condensed form, it's going to be H3C CH3, owing that each of the carbon is having equal number of hydrogen because this is a non-polar bond. In a non-polar bond, electron or atom are shared equally. But mind you, you notice that the way I write this H3, it was not in front of the carbon. It was at the back of the carbon. It is wrong for you to say CH3, CH3 because you have to understand rotation. There is always what we call levorotatory and dextrorotatory. Levro means left, dextro means right. If you are writing an atom to the left, you place the extra atom that are attached to the carbon at the back of the carbon. If you are writing to the right, then you place it in front. Because if you write it like this, it means this bond belongs to this hydrogen, and it's not possible. The bond at this middle is between carbon to carbon. So for you to overcome that challenges, bring this H3 to the back, giving you the expression you have on the board. Are you with me? So that is how to condense it. For this one too, since in a non-polar bond, electrons are shared equally, just let the 2 carbon catenate with each other. When carbon atom combine with itself, it is called catenation. You can write it down. Catenation. Catenation is a phenomenon that explains the ability of carbon to bond with itself. So for this one, since they are having 2 hydrogen, in a non-polar bond, electron or atom are shared equally. So you are going to share the hydrogen 2, 2. Then for this one, the carbon is 2, then the hydrogen is 2. It has to be 1, 1. But there's something you have to keep in mind in organic chemistry. Everywhere you see carbon, carbon must have 4 bonds. If you check this one, 1 plus 3, that's 4. 1 plus 3, that's 4. Since they are both sharing this bond, whenever you are counting a bond, you count for this carbon as if this one does not exist. So this carbon also belongs to this carbon. If you are counting for this carbon, you count this bond as if this one does not exist. So that's why I said 1 plus 3, 4. 1 plus 3, 4. So this one is balanced. All the carbon is 4, 4. But if you check here, there is only 1 bond between them, and they are having 2. This is 3 bond. And Here too, 1 plus 2, 3 bond. Therefore, it means this compound is unsaturated. That means by nature, alkane is saturated, while alkenes is unsaturated. What do we mean by unsaturation? It means the number of hydrogen that is needed is not sufficient, is not okay, is not enough. That is why we say that by nature, alkenes is unsaturated, because the hydrogen is not sufficient. That is why the concept of adding an extra bond comes in. So it is not as if it was because of the double bond we call alkene unsaturated compound. It was because they are naturally unsaturated due to their less number of hydrogen. That is why scientists now perceive that how can we overcome this challenge? Then the concept of introducing an extra bond now comes in. So when you now put an extra bond just to make them partially saturated, they can be saturated, but just to make them partially saturated, that's why we put this extra bond. This extra bond now is now called pi bond. So the one that is follow come, that is there, standby, is called sigma. And this is the symbol for sigma, like a sleeping six. And also, all the bond in alkane is sigma. So for the very first time, the first place where we see a pi bond is in alkane, because we notice that they are unsaturated. And for us to overcome this challenge, to make them partially saturated, we have to introduce an extra bond. So by so doing, if you count 1, 2 plus 2, that's 4. 1, 2 plus 2, that's 4. And in this context, in alkyne, there is already a bond. And if you notice, this is just 1, 2, 1, 2. For them to reach the 4 quota, it has to be what? We have to add 2 extra bonds. So that's why, in this case, alkyne now has 2 extra bonds added to the chain. Therefore, we are now having triple bond. So the 2 red bonds that I show, they are the pi bond. That means in every single bond, there is 1 pi. In every double bond, there is 1 pi, 1 sigma. In every triple bond, there is 2 pi, 1 sigma. But there's something you have to know. Sigma bond is stronger than pi bond. Sigma bond is stronger than pi bond. Sigma bond is stronger than pi bond. Just take this sigma bond as the bond that occurs naturally. It is created by God naturally. But pi bond is the work of woman. It is an artificial bond that we added when we notice that alkene and alkynes are not saturated. And therefore, it can be stronger than what is natural. Therefore, pi bond is weaker. But note, any compound that have pi bond in support of the sigma bond that already exists will be stronger than that other compound. The reason why alkene is stronger and more reactive than alkane is because apart from this single bond you see at the middle, alkyne, although the bond is weaker, but it has a little extra advantage apart from alkenes. So any bond that have pi bond in support of the sigma bond will of course be more efficient than the one that only have solely sigma bond. And for the case of alkyne, alkyne will be more, is more hierarchical, is more stronger than them, because apart from his normal sigma bond that everybody possesses, he has 2 extra pi bond to his bond. So that's why by nature of bond, these people are known for sigma bond in every single bond. In every single bond. But in every double bond, there is 1 sigma and 1 pi. 1 sigma, 1 pi. And in every triple bond, there is 1 sigma and 2 pi. That is the bond type. And also in the bond type 2, there is, this one is known to be having single bond. This one is known to be having double bond. So out of this double bond, there is 1 sigma and 1 pi. And out of this triple bond, there is 1 sigma, which is natural bond, and 2 pi, shown in red. You notice that alkane does not have a pi bond. No alkane compound has pi bond. But for the very first time, pi bond will occur when you have double bond, and pi bond will occur when you have triple bond. In terms of pi bond, alkyne compound has more pi bond than other compounds. In terms of bond length, you can answer that for yourself. Who do you think we have the longest bond length? Why? Because alkane is a 1 rope string. Well, let's say the same rope. Let's say you have a long rope. When the rope you have not coiled it is long, let's say it's 10 meters. By the time you actually double the rope, you curve the rope together, you see that the 10 meter will reduce to what? 5 meters. That means the most thinnest person will be the longest. So in terms of bond length, alkane is the longest because it is the most thinnest, while alkene is longer, and then alkyne is long. In subsequent videos, I'm going to continue with this comparison. Like we are supposed to talk about hybridization, their bond strength. We are supposed to talk about their reactivity and like that. So watch out for part 2, comparative chemistry of the aliphatic hydrocarbon. Please don't forget to subscribe. Share this video to anybody around you that you think need this knowledge. God bless you. Once again, I'm Phillips Olamide Oladele.